So, first question. We've got a tennis ball being thrown, and it's asking us to write down the equation that links kinetic energy, mass, and speed. This year, you get given all the equations, so you probably won't get a question like this. So kinetic energy is equal to half times mass times speed squared. Calculate the kinetic energy of the tennis ball at position C. Position C is right at the bottom. It's the moment the ball leaves the hand. So the person has thrown it and it's just left the hand. So all the information is given here. We've got the speed here. We've got the mass here. So we can just put it straight into this equation. So we can write it as KE is equal to half times the mass, which is 0.058 kilograms, times by the speed squared, 5 squared, which is basically 25. Anyone got a calculator? Can you work that out? Tell me what you get if you guys have a calculator. Not 69, no. Answer is 725, not quite 725. Make sure you put the right number of decimal places here when you put 0.058. It should be 0.725. If you got 725, you probably put 58 in there. 58 in the calculator rather than 0.058. This is triple and combined. Okay, so that's that answer. At position A, the tennis ball is at a maximum height. What is the gravitational potential energy of the tennis ball? What do you guys think you need to do here? So at position A, look at the diagram. So we just calculated the kinetic energy at this point. The question's asking to find the GPE here, gravitational potential energy. What do you guys think you need to do here? Yep, let me zoom in. 1 second. Zoom into this a bit as well. Okay, so people are making the mistake. Some of you've got it. So yes, the equation for GPE is mgh, but you actually don't need to use it. So it's here in the equation sheet, mgh, but you don't need to use it because you need to be able to predict basically the kinetic energy. All that kinetic energy is going to get converted into GPE. When you throw it, that kinetic energy is going to be converted into gravitational potential energy. Because think about what kinetic energy is. What type of objects have kinetic energy? What type of objects have kinetic energy, guys? Tell me. Moving objects, yeah? So the faster an object's moving, the more kinetic energy it has. What about GPE? How do you increase GPE, the gravitational potential energy of an object? How do you increase the gravitational potential energy? Yes, there will be a live on Wednesday. 8:30 probably. Height, yeah. So higher the object, the larger the GPE value. Okay, so think about what's happening to the ball. When you're throwing a ball, two things are happening. The ball is slowing down and as it's moving upwards, right? And the other thing is it's getting higher. So its movement is decreasing. So that means its kinetic energy is decreasing, but it's getting higher. So its GPE is increasing. That's because its kinetic energy is being converted into gravitational potential energy. So whatever we calculated here, so what was it, 0.725 joules is the same as the GPE here, because at this point here, there's no movement, isn't it? You know when something's at the top of its jump, there's a split second where it's got no movement before it comes and falls back down. At that point, there's no kinetic energy because there's no movement. It's not moving. So that means all of that energy is changed into GPE. Yeah, I use good notes. And yes, that'd be great if you could subscribe to my YouTube, guys. So yeah, the answer to this. So another clue, guys, if you get calculation questions like this and you get a 1 marker and it doesn't say calculate. See here, it said calculate. They want you to do a calculation. Here, they're literally saying, what is the GPE? And it's a 1 marker. So they basically, it's a clue to you that you probably don't need to use an equation. The answer's there somewhere, or it's a very straightforward answer. It's just 0.725. And here, write the units. They haven't given you the units here, yeah? Joules. This live is until 8:45. You should be given all the equations in physics. Okay, next one. Okay, this one's asking to write down the equation for GPE. So that's the one you guys told me about. GPE is equal to mass times gravitational field strength times height. That's given to you. So, next question. Calculate the height of the tennis ball above the tennis player's hand when at position B. When at position B. So this middle position, what do we have? We have the GPE at this point, right? At position B, the GPE is 0.38. So they've just told us this position is 0.38. So think about what's happening here. The ball is coming, what did they say? Yeah, the ball is moving up. So some of the kinetic energy is turned into GPE, but not all of it. So it's still moving. It still has some kinetic energy, has some GPE. All right. So this is how much GPE it has. So for this equation, to find out its height, you need to use the equation mgh. Right? So we need to rearrange the equation to get height as the subject. How do you make height the subject of this? You should get all the formulas, guys. Electricity, I do have electricity questions on this. If I don't get onto it today, then I'll definitely go into it on Wednesday. Divide by mg. Yep. So if you want to make h the subject, move the mg to the other side of the equation. So it's GPE divided by m times g, and put in all the numbers. So we've got GPE as 0.38. We've got our mass as, where was it? Here, 0.058. Times by G, 9.8. They've told us it's 9.8. So use whatever they give you. Use the value that they give you. Can anyone tell me the answer? .6 recurring. Yes, 0.6 recurring. So if you round that, you get around 0.67. meters, something like that. Where is 0.058 from? It is here. It's given to us as the mass of the ball, 0.058. Any other questions on this one then? Does everyone understand? These questions can be on both triple and combined. I think this particular one is triple, actually. I think there's a triple question, but the papers have, I think they have similar questions. So this might have come up on the combined paper as well. Where's 0.38 from? Here. It's given to us as the GPE. Okay? All right. Next question. Okay, so we do have an electricity question. So let's go through this. What quantity does an ammeter measure? So let's write this down. Ammeter, symbol for an ammeter. Capital A, circle. What does it measure? Current, excellent. What else can you say about ammeter? What other important thing? So it measures current. Anything else you guys can tell me about it? In series, yes. It must be connected in series. Then we got a voltmeter. Let me just write this as well. This one measures potential difference. Potential difference. This one needs to be connected in parallel. What's the difference between series and parallel? Anyone know the difference? Yeah. Series, all the components are on one loop. So everything connected is in one loop. Whereas in parallel, you have loads of different branches coming off. So components are on different branches. Components on different branches. Okay, so the question is just asking what quantity does ammeter measure? Current. That's enough to get that mark. Right, here we've got a calculation. Let's zoom into this. Okay, calculation time. Whenever you get a calculation, look at the information they give you. Try and identify what it is. There's one piece of information. That's one piece of information. And then look at what they're asking. So we've been given something in MA. What type of quantity is this? What is this? It says the current. So yeah, that's current. And then it says potential difference is 4.2 volts. So we need an equation with current, potential difference, and resistance. So looking at the equation sheet, which one would this be? Yeah, we do. Exactly, yeah. It's V equals IR. It's down here, this one. Let me put it this way around. This equation here, potential difference, V equals IR, okay? So look at the three things, write them down. If you struggle with this, write down all the things. So things they've given you and what they're asking you to find out, and then try and find an equation with all of them in it. this one is V equals IR. It's asking for R, so you need to rearrange the equation to make R the subject. R is equal to V over I. Right? Now, this is not straightforward because the current is in milliamps. All right? In this equation, if you want to use this equation, you need your current in amps. So this is why it's important to know what units each equation needs for it to work. So what I would do first is convert 3.5 milliamps into amps. Think of millimeters. How many millimeters are there in a meter? There are 1,000 millimeters in 1 meter, right? Same with amps. There's going to be 1,000 milliamps in 1 amp. So how many amps, how do you work out the number of amps for 35 milliamps? What would that be? Divide by 1,000. Yeah, so you have to divide by 1,000. So your first stage of your calculation is going to be 35 over 1,000, which is 3.5 times 10 to the minus 3. Now we've got all our values, we can put it into the equation. So 4.2 divided by 3.5 times 10 to the minus 3. And that gives... Thank you. So that should be 3.5 divided by 1,000, not 35 divided by 1,000. That wouldn't make sense. You get that value and divide it by 1,000. So what does that give, guys? Anyone calculated it? Thank you, Jazz. 1,200 ohms. Everyone okay with that? Any questions? Okay, let's move on. More electricity. Same thing again. Calculate the charge that flows through the thermistor. What does a thermistor do? Let's write that down. So we've got thermistor here. What does a thermistor do? So it was an upside down thermistor on that diagram, but yeah, you could draw it like that. Saying temperature is not enough. You need to say more. It's not a heater. Nope. It doesn't measure the temperature either. Nope. It doesn't control the temperature either. Kind of. Okay, you got to think of this as a type of resistor, yeah? Anything with this rectangle in it, I'm hoping you guys know that if you have a rectangle like this, that's a fixed resistor. Any diagram with a rectangle is a type of resistor, okay? So you get this, normal fixed resistor. You get this, which is a variable resistor. Then you got a thermistor. And then you get an LDR. Which looks like that. All of them have a rectangle in them, yeah? Except for fuse, forget fuse, that's something completely different. But all of these are types of resistors. So this is, okay, I think we've got the right answer. Yeah, it's a resistor that changes its resistance based on what the external temperature is, okay? So resistance is just something that slows down the flow of current. It decreases current. So in a fixed resistor, you have a fixed amount of resistance. So you have 6 ohms. It will always be 6 ohms all the time. A variable resistor, you can change the resistance of it. So you can go from 6 ohms, you can change it to 4 ohms, then you can increase it to 10 ohms, something like that. You choose what you change it to. So there'll be like a dial or something, you can turn it and you can choose what the resistance is. A thermistor is like a variable resistor, but you don't control it with a dial. It controls itself based on what the external temperature is. So if it's a very hot day, if you if you put it like near a flame or it's a very hot day, then its resistance is going to change. Its resistance is going to decrease. If it's cold, then its resistance is going to increase. And same with an LDR. It's a resistor that based this time not on temperature though, it's based on light intensity. So if it's in a very bright situation, if it's in a bright room, then its resistance is going to be low. But if it's in a dark room, its resistance is going to be high. Okay? All right, people are getting lost. Okay, let me repeat this and write this down. So these are all types of resistors. Okay, this is a fixed resistor. The resistance of this is always the same. You can't change it. This is a variable resistor. You can change the resistance of that. You control it with the dial. Thermistor is a variable resistor that is controlled by the temperature of the surroundings. So if the temperature of the surroundings is high, so if it's hot, if you put it near like a flame or something, then its resistance will go down. That's just the way it works. It basically does the opposite. So if its temperature goes up, its resistance goes down. Then an LDR stands for a light dependent resistor. It's exactly the same as a thermistor, but instead of temperature, it's to do with light intensity. So how bright it is, not how hot it is. So if the light intensity of the surroundings is high, so bright, resistance will decrease. Okay? Yeah, you can think of it as inversely. Wouldn't light affect its temperature though? You're assuming it doesn't. Light doesn't always, if you have a bright day, it doesn't always mean it's hot. Could you be asked to draw the symbol for 1? Yes, you can. I've seen the 1 markers usually. So you easily can get asked. Okay. So back to this question. So this is not even asking about what a thermistor does, but this is a question, a calculation where it's asking us to calculate the charge that flows in 5 minutes. So that is a time when the current is 3.5 amps. So we need an equation with charge, time, and current. So you look into your equation sheet, and I'm hoping you guys can tell me, yes, we got it. Some of you got it. It is this one here, Q equals IT. Charge is equal to current times time. So that's the equation. Q equals IT, it's the other way around. We need to make sure all our units are right, because in this equation, you need current in amps and you need time in seconds. So we have current in milliamps and time in minutes. So we need to convert both. So first of all, let's start off with the amps. How do we convert that divide by 1,000, not times by 1,000. Divide by 1,000. Let me write this down in the notes as well so that you guys don't make the mistake. So milliamps to amps divide by 1,000. Amps to milliamps times by 1,000. I'll let you guys screenshot this at the end. All right, so 35, let me not make that mistake again. 3.5 divided by 1,000 gives you 0.0035. 1, 2, 3, yeah, 0.0035 amps. Then for time, we've got 5 minutes. How do we convert 5 minutes into seconds? Yeah. 5 times 60 seconds in a minute. That gives 300, right? So now we put that all into our equation. We need to rearrange this equation. Do we? No, we don't need to rearrange it. It's Q equals IT. So we can just times these. 0.0035 times by 300 gives us, anyone? 1.05. Perfect. Well done, guys. 1.05 coulombs. Good. Okay, so next question is all about a thermistor. So it was important what I explained earlier. Explain why the potential difference across the thermistor changes as temperature in the house decreases. So this is what I was explaining. Temperature in the house, so that's the surroundings. Why would that affect potential difference? You need to first state what a thermistor does. Do you guys remember what I said? I said if temperature increases, something happens. This time temperature is decreasing. What's going to happen to resistance? Exactly. Resistance is going to increase. So let's go back here. We wrote here for thermistor, if the temperature of the surroundings is high, so if it increases, resistance will decrease. Just think of it as always doing the opposite, okay? In this question, it's saying the temperature is decreasing in the house. So that means resistance will increase. So you get a mark for saying that. Resistance increases. So we still haven't fully answered the question because it's asking why the potential difference changes. So we need to say how it changes because it hasn't said why the potential difference increases or decreases. What's going to happen to potential difference then? What model is my iPad? iPad Pro 12 point something inch, I forgot. Something like that. Potential difference and resistance, they're not the same thing. You got to think of this equation. Yes, it will increase. Think of the equation that we used earlier. V equals IR. Potential difference is equal to current times resistance, okay? So in this equation, imagine on this side, if you were to increase resistance, what's going to happen to potential difference? It's also going to increase, right? If you multiply two things and you increase one of the numbers, the other number is going to increase as well. So you say potential difference increases. That's your answer. Do you guys understand? Yeah. I will post this on YouTube, definitely. either tonight or tomorrow. I will. You guys will have, and I'll give you guys access to this sheet as well. You can print it off and try it yourself. I've got other stuff on YouTube as well, guys. So if you go onto the live exam walkthrough replays, we've done lives on radioactivity and electricity as well. So loads of questions on that. You can watch the video, and underneath in the comments, there's a link to the worksheet, so you can print it off and you can watch the videos while you do the worksheet. So check those out before Thursday if you want to practice some questions, and I'll upload this one as well with the questions. Okay. Thank you. Okay, so where have I gone? I have missed out a question. The circuit symbol shown in figure 3 can be modified to turn lights on and off by replacing thermistor with light-dependent resistor. Here, someone asked, here's a question. It's asking us to draw the symbol for an LDR. That's how it looks like. You can get away with writing bullet points. It's fine. All right, let's move on. So we got a question. Oh, did any questions on this stuff come up in chemistry? Plum pudding. So wait, someone said plum pudding came up, didn't it? Did it come up in the first paper? No, nothing on that topic. Oh, I'm getting a mix of answers. Yes, no, some alpha particles went through. Oh, it was in triple one. Okay, fine. Not in combined. Okay, sounds like it came up in triple, but not in combined. All right, fine. Remember, this can come up in chemistry and in physics, this topic. It's a bit of both. So that's what this question is all about, the alpha particle scattering experiment. What happened was, before this experiment happened, we believed the atom was a big positive charge with loads of negative electrons embedded within them. That's the plum pudding model. All right. So what happened is Rutherford did an experiment called the alpha particle scattering experiment, where he fired alpha particles at a thin gold foil. So thin gold foil, because you're basically assuming it's so thin that it's one atom thick. It's probably not one atom thick, but you can assume it's one atom thick. Okay, so when he carried out the experiment, he expected the alpha particles to go and basically stop, bounce off. But he was shocked because most of the alpha particles went straight through, as shown in this diagram. Most of them passed straight through, and that completely made this model not true, false, basically. So he disproved the plum pudding model because of that. Because if the plum pudding model was correct, then the alpha particle should bounce off, because this is like a solid sphere. But the fact they all went through told him one piece of evidence for the fact that most of the atom is made up of empty space. Okay, so that's one of the piece of evidence that he had. So most alpha particles passed straight through. And that proved that most of the atom is made up of empty space. Does everyone understand that point? Yeah. So the other thing that happened, what's the other? So this is 2 marks here. We got 1, 2 marks. What's the other 2 marks for? What are those lines on the figure? So let me zoom in. These are the paths of the alpha particles. So you can see alpha particles, most of them are going straight through. The gold nucleus is here. Most of them are going through, but what's the other thing? Exactly. Some of them are deflected. 3 of them are deflected in this diagram. So that's another piece of an observation that happened. Some were deflected by a large angle. So that just means like they weren't gradually deflected. Some of them just went straight back. What does that tell you? It's not about the fact that it's spherical, no. Yeah, there must have been something concentrated in mass in the middle of the atom, or somewhere in the atom, there's something that's concentrated in mass. Okay, so think about it. If most of them went through and one in a few deflected back, that means most of the atom is empty space. That's the only reason most of it will go through, right? But in there somewhere, there must be an area which is very concentrated in mass, and that's why the alpha particles started deflecting once in a while, not all the time. So you would say the atom contains, so that's basically the nucleus, right? So he discovered the nucleus of an atom. So it contains a nucleus that is concentrated in mass and charge. Okay? No, not triple. This is combined and triple. Everything in combined you can assume is for triple, but not everything for triple is for combined. All right, any questions on this, guys? This is chemistry and physics. I think this is the one thing which is in both. Yeah, you need to know all the other atom developments as well. You need to know about John Dalton, Niels Bohr, all of that. Okay, all right, moving on. So yeah, here we go, Niels Bohr. He adapted the nuclear model by suggesting electrons orbited the nucleus at specific distances. So he basically discovered that, yes, we have a nucleus. He accepted that. We proved that. Rutherford proved that. But electrons, he discovered electron shells, because this is what we do in chemistry, isn't it? We draw electron shells and we put the electrons in the shells. He discovered these. Before that, we didn't know that they did this. We just thought they moved around randomly. Okay? So, how does the distance at which an electron orbits the nucleus, how can it be changed? Anyone know this? This is tricky, this one. It's not like a really common question, but it is part of the spec. Not ionization, nope. Ionization completely removes electrons. Absorption, we're getting somewhere. Absorption of something. So what the question is asking is, how can you make an electron, because you can do this, you can make an electron go from one shell to a higher shell. So see this electron, how can you move it to a higher energy level, a higher shell? There is a way. Radiation, yes. This is something to memorize, guys. Okay, so you can do 2 things. Let's write this in our notes. It's unlikely to come up. Well, I'm saying that, but it's It's a very like small part of the specification. But if you want to go from a low energy level to a high energy level, so this electron, if you want to move it to this high energy level, that electron needs to absorb electromagnetic radiation. You can't, it's not heating, no. Has to absorb EM radiation. Let me write in full. If it's the other way around, what does it need to do then? Let me put this in a different color. If a high energy electron goes to a lower energy level, what happens here? What needs to happen for that to occur? Yeah, that needs to give off radiation, emit it. Good. Well done, guys. So high to low energy level. Has to emit electromagnetic radiation. Okay, so like I said, this is one of those things that barely comes up. It's a very small part of the spec, but like you just saw, it could come up. So in this question here, how many marks was it? 3 marks. So explain how distances at which electrons orbit the nucleus may be changed. So you can say the electron can absorb EM radiation to move to a higher energy level further away from the nucleus. Okay. All right. Any questions, guys? Let me go back to the notes so you can screenshot. That's what we've got there.